Welcome to Lecture 50, the lecture in which you will for the first time meet the quantum, the second of the really big new ideas of modern physics, an idea that grew not out of the mind of one person, as did relativity, but out of the minds and work and different approaches of quite a number of physicists through the early part of the 20th century, culminating in a pretty much firmly established theory of quantum physics by around the year 1930, late 1920s to 1930. Ideas that continued to grow, though, throughout the remainder of the 20th century and indeed continue to grow today into the 21st century. But we're going to look here in this lecture at the very basic idea of the quantum, and in doing so, we will manage to check off two more of those cracks in classical physics that I introduced back in Lecture 44. So let's begin and take a look at where we've been already in terms of classical physics and these cracks, these problems we had with classical physics. First, we had issues with the ether, these quandaries about trying to detect Earth's motion relative to the ether. We've resolved those. We resolved them with special relativity. We resolved the quandary of Mercury's orbit, that anomalous precession of Mercury's orbit, that 43 seconds of arc per century. We resolved that with general relativity. Both of those theories due essentially completely to Albert Einstein. Today we're going to look at glowing objects and electrons and light, and we will reserve the atoms for a later lecture. So let's move on and look at these cracks in classical physics. We're going to resolve all three of the remaining ones with quantum physics, but today, again, we'll look first at glowing objects, electrons, and light. So let me remind you of the ultraviolet catastrophe. The ultraviolet catastrophe was one of those problems in classical physics. It was the prediction of classical physics that there should be infinite energy emitted as you go to shorter and shorter wavelengths by any hot glowing object. And so it didn't really matter whether I turned the current up or down or what. As long as the object was above absolute zero, it should be putting out infinite energy, and most of that energy should be in the shortest wavelengths, which at the time were known to be ultraviolet. Clearly a contradiction with what actually happens. The observation is that the energy peaks, as we said before, at a temperature-dependent wavelength. So if I make the temperature hotter, not only do we produce more energy, but not an infinite amount, but we also produce an energy whose dominant wavelengths tends to be toward the shorter wavelengths. Here we have a yellow-white. Here we have a kind of orange-yellow. Here we have a kind of dull red. So those are the observations. The theory is at strongly contrasting odds with the observations. So how do we resolve this? Well, the resolution came in 1900 by Max Planck. And Max Planck was a German physicist. He was quite conservative in his approach to physics, and he really didn't quite embrace the revolutionary idea he put forth here. But here was Planck's resolution. The classical prediction, based on classical electrodynamics and classical thermodynamics, suggested that the radiance, the amount of power emitted per unit wavelength interval by a hot glowing object, should depend on the temperature, and it should go as the inverse fourth power of the wavelength. And there's where that ultraviolet catastrophe is coming from, because if you make the wavelength lambda, the thing in the denominator here, again, the Greek lambda is our symbol for wavelength. You'll remember that from the lecture 18 on waves. If you make lambda smaller and smaller, that radiance just goes up and up and up toward infinity as lambda goes toward zero, and that's clearly not what happens. If you look at the actual curves here for the 6,000 Kelvin and 4,000 Kelvin glowing objects, you find that the radiance goes up, it peaks, and then it drops down to zero at zero wavelength. Planck had to figure out how to make that happen. And he figured out how to do it mathematically. So he had to somehow get rid of that blowing up as the wavelength goes to zero. Well, he came up with a different formula. And his formula looks a lot more complicated. And I'm not going to prove this, but in fact, for long wavelengths, large lambdas, it reduces to the classical formula. That may not look obvious, but for those of you who know a little bit about expanding functions, if you expand that exponential, you will get a term with a lambda that cancels the lambda to the fifth, or 1 over lambda that cancels that lambda to the fifth, and you will get a lambda to the fourth in the denominator, and it will end up looking just like the classical formula. But as you go to shorter wavelengths, Planck's formula deviates from the classical prediction. Now, I want to emphasize, Planck is making up a formula that he is trying to get to fit those actual observed curves of radiance versus wavelength. You'll notice something important in this formula. There's a constant in there which is designated h. It's now called Planck's constant, and it is the fundamental thing about quantum physics. If Planck's constant were 0, if we lived in a universe where Planck's constant were 0, this formula would reduce to the classical one, and we would have no quantum effects at all. Planck's constant is the constant that tells us our world is quantized. And what Planck did was simply adjust the value of that constant, which you'll notice appears in two places in his equation, in that exponential and also in the numerator. And he adjusted it so the observed curves were fit. And he found the value of that constant had to be very small value in SI units. It's 6.63 times 10 to the minus 34, and its units are joules times seconds, which happen to be the units of something called action. They also happen to be the units, as we'll see, of angular momentum. So it's a constant, a fundamental constant of nature, a new fundamental constant of nature, like C, or like the Coulomb constant K, or the magnetic constant mu naught, or the gravitational constant big G. H is a new constant of nature that gets introduced with Planck's resolution. Now, let's look at the implications of Planck's resolution. Right now, it's just a mathematical exercise. Let's make up a formula, says Planck, that will fit the observed distribution of radiation with wavelength, and that will reduce to the classical prediction at long wavelengths away from the ultraviolet catastrophe. So he makes up this formula, he finds that he puts a new constant in it, he adjusts the value of the constant for the fit, he finds that the value of the constant is 6.63 times 10 to the minus 34 joule seconds. What are the implications of this work? Well, the mathematical implication is that there is a term now in the denominator that has e, the base of natural logarithms, the basis of the exponential function. It's being exponentiated to a power that involves some constants here. You can see the constants include the Planck's constant and the speed of light. And down in the denominator is lambda. And as lambda goes to 0, or gets smaller and smaller, that exponent gets bigger and bigger. E to a big number is really huge, and that term blows up exponentially as lambda goes towards 0. And even though we've got a lambda to the fifth outside of that parentheses in the denominator, and the lambda to the fifth is going to 0, you might say that's going to make the whole expression go to infinity. In fact, the exponential blows up so much faster than that lambda to the fifth goes to 0 that the whole denominator goes to infinity, and that reduces the radiance to 0. So the mathematical implication, the reason this works, is that the radiance is then reduced to 0 at small wavelengths, and that's exactly what you see in the observations, and that resolves the ultraviolet catastrophe. Our light bulb glows calmly with whatever radiance it's supposed to have for its given temperature, and it doesn't produce infinite energy, and it doesn't produce most of its energy at short wavelengths, because this formula mathematically takes that down to 0. That's the mathematical implication. What about the physics implication? Because we're about physics here, not just about mathematics. The physics implication, and this is the one that Planck had trouble accepting. What this implies is that the energy of the atomic and molecular vibrations, which after all are what are causing a hot glowing object to radiate energy, back again to our study of heat and thermodynamics, we know that the internal energy associated with temperature and heat is the energy of random motions of atoms and molecules vibrating in place in a solid or whizzing around in a gas or liquid. And we know from electrodynamics, from studying electromagnetism, particularly in Lecture 40, that the source of electromagnetic radiation is accelerated electric charge. So these atoms and molecules whizzing around, and they do have electric charges in them, they're the source of the energy that gets radiated away. The implication of Planck's constant is that the energy of those vibrations is quantized, and it comes in multiples of a certain fundamental amount, and that fundamental amount turns out to be Planck's constant times the frequency of the vibrations in question. And I'll say a little bit more about that in just a moment, but let me simply point out how this solves the ultraviolet catastrophe for us. It means that the minimum amount of energy at very high frequencies, which correspond to very short wavelengths, because frequency times wavelength is the speed of light c, very high frequencies, the minimum amount of energy is so large that you're very unlikely to have any atom with that amount of energy, and so you simply get no radiation at very short wavelengths. And that's physically how quantization, the idea that the amount of energy at a given frequency of vibration comes only in multiples of a certain minimum amount, that idea solves the ultraviolet catastrophe physically in the way, and it's related to the mathematical way in which this new term involving Planck's constant solved the problem mathematically. So those are the implications of Planck's formula. And the big form, we're not going to worry about Planck's formula much more here, but we are going to worry about that little formula at the bottom. And let's take a look at that formula. Let's do an anatomy of an equation like we like to do. This is a pretty simple formula. We're going to do two anatomies of it in this lecture. It says E equals HF. What does that mean? F is the frequency of an oscillatory process. In this case, the frequency of atomic and molecular vibrations that are taking place in a hot, glowing object. E is the quantum of energy at that frequency, meaning E is the minimum amount of vibrational energy these objects can have. Now, this is a very non-classical idea. In classical physics, I put a mass on a spring, which would be the analogy of a vibrating atom or molecule, and I can give it any amount of vibration I want. It has a certain frequency set by the spring and the mass, but I can give it any amplitude I want. This formula says, no, you can't. It says you really can only give it certain multiples. You can give it an energy that's a multiple of this fundamental amount that comes from multiplying Planck's constant by the frequency. Now, for a macroscopic mass spring system like I might make here in the laboratory, H is so small that I don't notice that fundamental quantum, although I'm going to show you a little bit later an example where an almost macroscopic object has been made to vibrate and the quantum of its oscillatory vibration is actually evident. Anyway, quantum of energy for frequency F, the minimum amount of energy you can have in a vibration at that frequency is on the left. On the right is the frequency, and the proportionality constant, again, is this Planck's constant, 6.63 times 10 to the minus 34 joule seconds. So Planck has resolved for us the ultraviolet catastrophe. No more ultraviolet catastrophe, but in doing so, he's had to introduce a great big new idea, the idea of quantization. And in this case, what's quantized is the vibrational energies of oscillatory processes like atomic and molecular vibrations. And I'm being a little bit vague in describing that for reasons that you'll see in just a moment. Because what we would like to do next is move on and look at another one of those cracks in classical physics, this one involving the interaction of electrons and light, and we're going to see that the resolution of that is also going to involve quantization. So let me remind you of that one, which was a little bit more complicated. It involved this interaction of light with electrons where we had metal plates in a sealed, evacuated tube. We shine light on those metal plates. Electrons are ejected from the metal by the energy of the light, and we hook up a battery and a meter, and we're able to attract electrons if the left-hand side of the battery, as shown here, is positive, so it's connected to that left-hand plate. The electrons are ejected from the right-hand plate. Electrons are negative, so they come flying out and go toward the left-hand plate, and there's a little meter registering that an electric current is flowing through this complete circuit. And as we argued in Lecture 44, it should take a while for the electrons to be ejected because it takes time for them to absorb enough energy from the light wave where the energy is spread out all across this extended wave. Increasing the light intensity should shorten that time because it takes less time because there's more energy available. The electron energy shouldn't depend on the light's wavelength. Those are things we thought should happen on the basis of classical physics. What in fact happened, as I pointed out in Lecture 44, was that the electrons were ejected immediately. The electron energy did depend on wavelength. In fact, it increased with decreasing wavelength. And there was, in fact, a cutoff wavelength, a longest wavelength, longer than which you could simply not get electrons to be ejected at all. So the actual observations of this photoelectric effect, the interaction of light, photo with electrons, photoelectric effect, is a complete contract with classical physics. By the way, the photoelectric effect provided the first example of a kind of electronic light detector, a so-called electric eye. And in the old days, early part of the 20th century, when you walked through an automatic door that opened, seeing your presence, you were interrupting a light beam that was falling on something like this photoelectric cell. That's long since been replaced by all kinds of solid-state electronic devices, but this was an early way of detecting light electronically using the photoelectric effect. Well, how do we look at this photoelectric effect? How do we understand it? How do we realize what's going on? Well, let's take a look first at some data here. So I've plotted a graph here that shows on the horizontal axis the light frequency in units of 10 to the 14 hertz. So we're going from about 4 to 12 times 10 to the 14 hertz. And up at the top, I've plotted the corresponding wavelength, which goes from about 700 nanometers, 700 billionths of a meter, down to about 300 billionths of a meter. We're spanning from the infrared to the visible to the ultraviolet across this graph. And you'll notice now in the lower right diagram, I've reversed the battery. So the negative is now to the left. And that means that left-hand electrode in that tube is going to repel the electrons that are coming out of that electrode, that are being ejected by the light. But if those electrons are ejected with enough energy, they may still be able to overcome that repulsion and make it to that electrode, and there will still be a little bit of current. And in fact, if I crank up the battery voltage, then that repulsion will get bigger and I will repel the electrons more. And so there will come, for any amount of light coming in, any color of light coming in, any wavelength of light, there will be some voltage that I can apply with that battery that will stop the electrons, that will stop the current, that will keep the electrons from reaching that plate. And that's called the stopping potential. And so that stopping potential becomes a measure of the energy with which the electrons were ejected from that plate. And so in this graph, what you're seeing is the stopping potential on the vertical axis versus the light frequency on the horizontal, or equivalently the wavelength on the top horizontal axis. The stopping potential is measured in volts. And what you see is down at the lower left, there's a cutoff. There is a place at which the stopping potential is zero. Electrons, even at zero voltage, even not trying to repel them, they don't come out of the metal. So that's that cutoff frequency or cutoff wavelength, below which frequency, above which wavelength, no electrons are ejected. We need to explain that. And then, as the frequency of the light goes up, the stopping potential that you need to stop those electrons, and therefore the energy with which they're being ejected, increases linearly. And we need to explain that. Now, these experiments, again, were done in the late 1800s through into the 1900s. It was in 1905 that Albert Einstein explained these results. What is the resolution? Einstein's 1905, another one of his famous papers, the one that was named most prominently in his Nobel citation. He says, let's consider that light consists not necessarily of waves, but now of little bundles of energy. The energy is bundled in little discrete particle-like bundles called photons. Big idea in physics, the photon, a light particle, if you will. The photon energy, same formula that Planck had, is E equals hf. How does that explain the photoelectric effect? Well, there's a minimum energy needed to eject an electron to get it out of the metal, because the metal is holding on to it with electrostatic forces. And so there is a minimum frequency required because the photon energy is directly proportional to frequency. Minimum light frequency. That corresponds to the cutoff wavelength. The electron energy increases with increasing frequency because the photon energy increases with increasing frequency, the energy of these light bundles of energy that are coming in to eject the electrons. The current depends on the intensity, but the electron energy doesn't depend on the intensity because the current gives us the number of these photons. And the electrons are ejected immediately because instead of this being an interaction where it takes a long time to absorb energy from a wave whose energy is all spread out, in fact, the interaction is with a little bundle-like concentrated lump of energy that hits an electron and ejects it almost immediately, regardless of how intense or not intense the light is. And so we have the same equation again, E equals hf, applied now to something different, to light rather than atomic vibrations. So we're going to do the anatomy of this one, and it's very similar. F is a frequency, except in this case it's the frequency of light, which is c over lambda if you want to express it in terms of wavelength. So that's a frequency. This is an energy. In this case, it's not the energy of a molecular vibration, but the energy of a photon, one of these little bundles, these particle-like bundles of light energy. And h, again, is Planck's constant, 6.63 times 10 to the minus 34 joule seconds. Let's do an example. Since we're quantitative in this course, let's do an example where we look at this photon energy. So let's go over to our big screen. So let's take a look at what this concept of the photon and the photon's energy being proportional to its frequency means. What do we mean by the frequency of a particle, by the way? We'll get to that more in subsequent lectures. So here's a problem I'm posing. Photon energy. Find the photon energy and find the number of photons emitted each second by three things. A 1-watt AM radio transmitter. The AM radio band spans about 550 to 1500 kilohertz, 0.5 to about 1.5 megahertz, so we're sort of right in the middle of the AM radio band with a frequency of 1 megahertz, 10 to the 6 hertz, a million cycles per second. A 1-watt LED night light, such as you might plug into your hallway so you can have a little bit of light at night. 1-watt LED is a light-emitting diode. We'll see a little bit later how they work. They're a quantum device. And their frequency is a frequency in the visible light range, about 5 times 10 to the 14 hertz. That is consistent with the frequencies I showed you on that data from the photoelectric effect. And finally, a dental X-ray machine producing a watt of X-ray power. Typical X-ray frequency is on the order of 10 to the 19 hertz. So we want to find two things. We want to find the photon energy, and then we want to find the number of photons emitted each second by each of these three devices. Notice they all have the same power. That is, they emit the same amount of energy every second. But they're going to have different photon energies because they have different frequencies. So here's our big, massive idea here. The quantization of the energy of light, if you will, the vibrations of the light waves of light somehow result in these quantized bundles of energy whose energy is proportional to their frequency, E equals hf, just like Planck said, the quantized vibrations of the atoms and molecules resulted in these basic measures of energy that you could have for those vibrations. So any kind of vibration or oscillatory process, that's why I use that vague term oscillatory process. So E equals hf for our photons. Let's do the numbers. For the radio wave, or the radio photon I should call it, it's Planck's constant, 6.63 times 10 to the minus 34 joule seconds, times 10 to the 6 hertz. And by the way, hertz is an inverse time. It's a per second. So that hertz cancels the seconds. And we have 6.6, I'm rounding it off here a little bit, times 10 to the minus 28. We got minus 34 and plus 6, that gives us 10 to the minus 28. And I just lopped off the 3 to keep two significant figures. So each photon in that radio beam has a tiny, tiny amount of energy, about 10 to the minus 27 joules, 6.6 times 10 to the minus 28 joules. Do the numbers for the light. Well, it's the same calculation. We can do arithmetic. It's 6.63 times 10 to the minus 34 joule seconds times 10 now to 5 times 10 to the 14. We get 3.3 times 10 to the minus 19 joules. That's a lot more. That's 9 orders of magnitude bigger, approximately. And we do it for the X-ray, and it's 6.6 times 10 to the minus 15 joules. Now, those are the energies of the individual photons. So clearly, to get the same rate of energy, we're going to need a lot fewer X-ray photons than we are radio photons. Power is energy per time. That's what that 1 watt is. 1 watt is 1 joule per second. So the number of photons per time is the amount of energy per time, the power, divided by the photon energy. So for the radio photon, it's 1 watt, that's 1 joule per second, divided by that energy, which was 6.63 times 10 to the minus 28 joules per photon, and that comes out 1.5 times 10 to the 27 photons per second. So in that very weak 1 watt radio signal, we've got 10 to the 27 photons coming by every second. Light, it's less. It's only 3 times 10 to the 18 photons per second. And X-ray is even less. It's about 1.5 times 10 to the 14 photons per second. Now, I want to make an important point based on this. I recently got a question, actually, from a viewer of one of my other great courses saying, oh, is it the case that for frequencies below this, everything is a wave, and above this, everything is a particle? And I said, not quite that simple. At very low frequencies, like the frequencies associated with radio waves, 1,000,000 times a second, that's a low frequency as frequencies go, it takes so many photons to make up any appreciable beam with any appreciable power that you don't notice the discreteness of the energy bundled into these photons. But as the frequency goes up, it takes fewer and fewer photons to carry the same power, and so you notice the quantization much more. That's why we tend to notice quantum effects with X-rays when we don't notice them with radio waves very much. And visible light is somewhere in between. Sometimes we see quantum effects and sometimes we don't. You can actually, in a very darkened room, detect slight fluctuations in the light level, which are statistical fluctuations in the number of photons. So at low frequencies, we need lots of photons to get a given power. At high frequencies, we need fewer. Okay, let's move on and look at one more example. This is also electrons interacting with light. It's not one we talked about before, but it's going to reinforce this photon idea. Here's the idea. How does light interact with electrons? Well, classically, here's what we would predict. We would predict that electromagnetic waves are coming in, and now I'm going to picture an electron that's just sitting there, sort of stationary, free electron. It might be bound loosely to an atom or something, but in come these electromagnetic waves. They're incident on the electron. The electric field of the electromagnetic wave, electrons respond with their charge to the electric field, and they oscillate back and forth. And they oscillate at the same frequency as the electromagnetic wave, because that's what's causing them to oscillate. And we know that accelerated charge, and an oscillating charge is certainly accelerated as velocity is changing. Accelerated charge is the source of electromagnetic radiation, and so that electron emits electromagnetic waves in basically all directions. Not quite, it doesn't emit it right along the direction of acceleration. But here's the crucial point. Those waves are emitted with the same frequency, and this is a simplified description of the process of an electromagnetic wave scattering off electrons. If you had a region where there's a lot of electrons around, the light waves would scatter off and light would go off in all directions. And the key thing is it would go off with the same frequency it came in with. But that's not, in fact, what happens. Instead, what happens is something called the Compton effect, which was discovered by Compton in 1923. And the Compton effect really provides a reality for these photons. In the Compton effect, a photon collides with an electron. So that yellow particle coming in is a photon. It hits the electron recoils, the photon bounces off, and because the electron has picked up some energy, just like a collision of two billiard balls, although it's a collision you have to handle with relativistic mechanics because the photon is moving at the speed of light, you have given some energy to the electron, and the photon goes off with less energy. And that means it has a lower frequency by E equals hf, and therefore it has a longer wavelength. So the fact that when you do one of these scattering experiments, you observe a longer wavelength coming out is a really good clue that the interaction between the light and the electron is particle-like rather than wave-like. Now, it turns out that just looking at, say, visible light isn't going to show that to you because it takes really short wavelength, high-energy photons to make this possible. Because the Compton shift in wavelength turns out to be on the order of Planck's constant divided by the mass of the particle that's getting hit, in this case the electron, times the speed of light. And that's a very small number. It's about 2 picometers, 2 times 10 to the minus 12 meters. Let's do a quick calculation that shows us how that works. So here we are at our big screen again. At what wavelength and frequency will this Compton shift be readily measurable? Let's say 5% of the original wavelength. And let's ask, where is this in the electromagnetic spectrum? So we know the wavelength shift is about 2.43 picometers. By the way, that quantity is called the Compton wavelength of the electron. The shift depends on at what angle you're looking, but it's on that order. We want to know the wavelength of which that's 5%. So 2.43 picometers is going to be 0.05 times some unknown wavelength lambda that we're going to solve for. So lambda becomes 2.43 picometers divided by 0.05. Do that out. You get 49 picometers, 4.9 times 10 to the minus 11 meters. F is c over lambda because frequency times wavelength is the speed of a wave. That comes out 6 times 10 to the 18 hertz. And where is that? Well, here's our electromagnetic spectrum that we saw back in lecture 40. And if you look at where that lies, that frequency of 6 times 10 to the 18 hertz, or equivalently that wavelength of 49 picometers, it's here well into the X-ray region. So you are not going to see the Compton effect with visible light. You might barely see it with ultraviolet, and you're not going to see it with radio and TV and microwaves and infrared. You're not going to see it with visible, but you will see it with X-rays and you will see it with gamma rays. By the way, the Compton effect works in reverse too. If you have a high-energy electron and it interacts with a photon, the electron will give up some of its energy to the photon and you will shift the photon frequency upward. And that's one way that nature makes high-energy gamma rays. Astrophysicists are now beginning to look with gamma ray telescopes above the atmosphere, and they're seeing gamma ray sources that are resulting from the so-called inverse Compton effect, where the electron with high energy gives its energy to the photon, and the photon energy increases. And medical practitioners or medical technology people are now beginning to exploit that effect to make high-energy beams of gamma rays for so-called gamma cameras and other medical diagnostics that involves gamma imaging. So the Compton effect is actually something useful, but for our purposes, it's something that convinces us that photons are real, that light interacts in a particle-like way, and that that's more prominent at these high frequencies. Okay, well, let's wrap up. Our summary consists of a big fat formula. E equals hf, the quantization of any kind of vibrational oscillatory process, whether it's an electromagnetic wave or atomic and molecular vibrations in a hot glowing object. It's quantized according to this formula. The minimum amount of energy you can possibly have in such a system is its frequency times that tiny Planck's constant. By the way, notice that all energies are allowed because all frequencies are allowed. But given a frequency, of vibration of an electromagnetic wave, you're stuck with a minimum amount of energy you can have. Atoms and molecules, that's verified by blackbody radiation, the radiation from hot glowing objects. Light and other electromagnetic waves, it's verified by the photoelectric and Compton effects. And we have inherent here a very new fundamental constant of nature, Planck's constant H, 6.63 times 10 to the minus 34 joule seconds. And a way of thinking of Planck's constant is it's establishing for us a kind of graininess of nature at the smallest scales. Nature is not continuous, but has a discreteness at the smallest scales, a graininess, and that's what quantization is all about.